Thank you. So we had a lot of fun. I had a lot of fun discussing this and disagreeing vehemently with Christian here. Um, Ultimately, our disagreements, I think, were very productive in that they led to two architectures that both approach the problem from of a molecular printer from two different directions. Um, so where are we? Do you want to explain your idea first?
Yeah, so the idea of uh, having a probe tip that's got something on it that you're going to bring onto a part or a product that you're trying to build from little bricks, bring one brick in, position it, lock it in, pull away, and then bring in another brick. I wrote a proposal in the working doc in 2007 in one of these in the Foresight roadmap for productive nanotechnology. And the thing that I want to bring to it that's new is that we can build the bricks now out of spiroligomers. I've got the chemistry and the software to do it, and the bricks can be functionalized on the outside so that they can snap together. And then I just pulled in the proposal that I had from 2007 of how we would grab the bricks, put them in position, connect them, pull away, and then get another brick and bring it into position.
Okay, and then the second design approaches this from a different angle rather than go through the picking up and moving and putting it down. Instead, what we would do is use tips or tip arrays to locally induce a reaction. So the same idea of complementarity between chemistry, between the components you're bringing in and what's already been assembled is common to both ideas, but in this latter idea, the reactions do not proceed spontaneously. Rather, you use these tip arrays to locally induce a reaction. So the reaction is not spontaneous, and the tips are solely used to activate the reactivity. And what that does is it circumvents the issue of picking up and moving reactants. However, in that particular case, you could have issues with achieving the same spatial resolution, but it might be easier to implement. So I think, both ideas are worth pursuing. And as you go down the pathway, as we all know, unexpected challenges will arise, and we don't know which of these two approaches will have the greater challenge to implementation. But I think the good aspect of both is that they're both ready to be pursued. There's no major barrier that needs to be overcome to start exploring these ideas.
And so moving on down, did we lose part of it here? No, we got that part. Okay, so just moving on down the topics here. So describe the architecture, and then 4 biggest unanswered questions. So one thing is, I'm not talking about picking anything up. I was thinking of more, I'm planning to flow things by capturing them from solution, flowing a lot of material by capturing one molecule from solution and then placing it on the surface. And then when you pull it away, you'd wash that thing off and you'd flow in another one and just capture it from solution. So you don't need to take the tip to pick up a piece. But even that, the cycle of capturing, binding to the surface, waiting long enough to ensure that the chemistry is complete or as close to complete as you need, could be long. And so that will limit how complex the product is, because you may only be able to do 30, 40, 50 cycles, and that may limit the size of the thing that you want to build. Did you want to add anything to that?
No.
Okay. And then what are the biggest risks? We heard yesterday about probe tip microscopy with single atoms. If you're working with bricks that are like 2 nanometers across, 2 by 2 by 2 little brick made out of spiroligomer structures, you'd need to position them still within like a few angstroms. And I just don't know much about the probe tip capabilities, whether that is possible. I see people manipulating tips to within an angstrom to image atoms, but can you bring something in big and bring it in just the right place to within a few angstroms to make the chemistry happen is an open question for me. There's some more issues there. That was kind of the big one. We initially started talking, or did you want to add anything to that? Okay, we started by talking about killer apps, and the thing I think about is with a probe tip sort of assembly, you can only make one thing at a time. With parallel probes, maybe you can make more, but let's just say one probe tip, make one thing at a time. What's valuable to make there? And one thing we thought was nanopore DNA sequencing. If you can make a precise pore that you could use for sequencing DNA, like Oxford Nanopore is a company that does this with a protein, then one really good DNA sequencing pore could sequence a lot of DNA. Adam suggested ultimately down the long term, we could print cells atom by atom. We could do combinatorial.
I can explain this one.
Good.
What's the big benefit of these printers? We can already make a lot of structures with very narrow line widths using clean room techniques, but a lot of the materials you want to work with, proteins, DNA, et cetera, are incompatible with clean room methods that are going to denature or destroy these materials. So a lot of the applications we're thinking about are soft material, complex architectures. But we also try to think, what's a 3-month application that we can work on now, what might take 3 years, and what might take 30 years. So some of these are shorter term, like the nanopores, combinatorial arrays. But if you truly had a versatile architecture, what would preclude you from doing something like printing a cell that recapitulates the complexity of a cell? So that's my thoughts, and there was some pushback on that, which I think is reasonable. But you might as well dream big.
Are we done?
1 minute.
1 minute. What does a minimum viable implementation look like? I can synthesize bricks now. We would need to get a team together to synthesize, design a bunch of bricks that are compatible with each other, that are linked up with each other, people to build the probe tip assembly, test all that stuff out, and then start building something like just link 2 things together on a surface, then 4, then something would have maybe 8 parts to make a nanopore. That would be a minimal viable task, I think. Anything to add there?
Nope.
Okay, and then pictures again, and then what work needs to be done. Wait, do we even miss that one? Probably.
Yeah.
Yeah, and what can we do with a 5K development grant? Argue some more about it.
Yeah.
All right?
But with alcohol.
Yes.
Thank you.
Any questions? No.
Well, first, is there any kind of like question of understanding before we get into the discussion problems? Yeah.
So I missed the distinction between the two methods here.
The major distinction is the following. In one method, the tip is literally used to move molecules into position. In the other method, molecules are floating around in solution, and the tip locally provides energy that's going to drive a reaction. That's the fundamental difference.
Good.
So since this approach is highly dependent upon tips, and we heard a little bit about atom by atom tips, does a tip exist that can manipulate a macromolecule? Does a tip exist that can position a macromolecule in sufficient configuration that it would react with, the pieces that are already down on the surface? So that was a question.
I've seen people, pull DNA and squish proteins. I think so. And the guy who makes tips is nodding yes, so I feel good about that. Yeah, okay, so I can make nanoparticles that are 2 by 2 by 2 nanometers.
Inorganic nanoparticles. I
I'm-
mean biological molecules.
Yeah, I'm talking about organic, not biological, stiff organic things made out of like 3 or 4 spiroligomers lashed together through covalent bonds to build something that looks like a bundle of logs.
But there are certainly examples in the literature of tips being used to move biological macromolecules. Extensive literature
Yeah.
for that.
Yeah, do you want to comment on it at all? I think you had your hand up as well.
Nothing beyond what I said.
Ah, okay.
You
Mark?
have a question?
Just real quick, for the positional one, not the solution one, but the positional one, are you imagining that in solution or in vacuum?
In solution.
And is that a requirement of the chemistry here? or-
Yeah, because I don't want to worry about picking things up, because I just trying to make it a little simpler. So in solution, you can
Right.
flow things over.
So I'm sorry, but I'm thinking about the other one where you are picking things up. Like, does the chemistry require that this be in solution, or is it do your molecules change shape when they're, desiccated?
It wouldn't change things. It'd just make things a little more difficult. It would
Okay.
make it a little more difficult, but I don't think it's impossible to pick things up. Yeah.
Thank you.
Okay, well, should we
Wait,
go
one
to...
last question.
Yeah,
In the back,
we-
he's had his
Yeah,
hand
I
up.
have a challenge
No,
to this.
behind you.
Okay.
Sorry.
Challenges tip thing.
So if the additive technology is too complicated, would it be easier to do subtractive technology? Like I'm thinking Minecraft was spiroligomers.
Well, if you want to build something complex, that would mean starting with something complex and then carving it down. And
then
Like
adding
layers
back
of
up.
different.
yeah, I think adding back up will give you more flexibility with what you build. I love Minecraft.
I'd love to get to the discussion prompt as well. You can stay right here. Now it's also time for others. What do you think is really good about this proposal? Anything you want to highlight here, or anything that still needs work?
That seems to be the closest thing to being possible.
The closest thing to be impossible. Do you want to challenge a particular part of it, or no? Any other bits on like what's okay, Mark?
This is a follow-up to what I asked before, because I think if you're doing this in solution, obviously you're doing it at higher temperatures, and then there's Brownian motion, so you're introducing a lot of error here. What I like about this approach is that you're using large molecules, and therefore your positioning does not have to be as accurate. But I feel you kind of lose that since you have Brownian motion and higher temps. So if there's some way that this could be done at lower temperatures in vacuum or something like that, it'd be much, much more reliable in my mind.
I think both of us are kind of thinking that I won't speak for someone else, but if you have groups that would react together only when they're held close together and pushed together for tens of half-lives of the time it takes for them to react, then you can get reliable chemistry happening. And the Brownian motion thing is really just I don't see that as a big problem when you're manipulating larger things, but it is an open question whether it could work or not.
Any
Nobody's-
other criticisms or appraisals that you want to? Okay, well, last one. Who else do you know that should be working on stuff like that? Is there anything that you in particular could be doing to help it along? Like, do you know anyone else who's working on similar things that they should be talking to?
Just in talking to scanning probe microscopists, just getting
I would like to talk to probe people, especially about making tips. It's something I've proposed in the past, and we could make them now. Or would they still be too wiggly? If you're worried about carbon monoxide, then my things are probably still too jiggly wiggly.
I very much focus on the vacuum set. There's a whole scanning probe community.
Okay, then I would like to talk some more. That would be wonderful.
Just a question maybe related to what other type of person you might need, but how do you know that you've added the thing? Is there some metrology or something that's required?
Good. If you flow in a brick that you're going to place and then lock, chemical reactions will lock it in, then you pull it away with a broken, gripper that you would then release, You could then flow in a tip that you would use to image what you just put down, to see if it's there, to feel it. And if you don't feel it, then you can flow that brick that you didn't get in there back through again and try it again. And so you have the ability to do that kind of error correction in principle. So in the thing that I wrote in 2007, sorry, and nobody's read it, hardly anybody reads it, but the attachment and the disattachment was through redox chemistry. You can oxidize and reduce the tip and selectively bind something that flows through, and then release it by oxidizing it, and then it's ready to do that again. That's how you would do it.
Okay, thank you so much.